Welcome to High Performance Computing, Advanced Scientific Computing. Today we have our practical lecture 1.1 about an introduction to C programming and to scheduling. So basically both of them are really, let's say, very short introductions. So we continue a little bit what we learned from practical lecture 0.1, if you remember, a little bit on Unix skills, module, the whole environment that we have in HPC. And we'll build on this and use a module environment to compile a C program. And obviously, this course is not called C programming, but high performance computing. So we keep the C programming details really to the necessary few, mostly because we want to later then, after we have seen the conceptual material of lecture 2, then also the practical lecture 2.1, where we will have our first MPI program. If you remember, MPI was a message passing interface and so on. Scheduling then is an important concept that we will also learn in the course essentially today in the second part, where we understand that we have a multi-user environment in HPC and we need dedicated HPC system software to make that work together with other users. But before we start to go into the material of this lecture, let us review what we had the last time. So this was really a high level, if you want, introduction to high performance computing the last time. Lecture 1, really the first time, let's say, looking what HPC has to offer. And of course, also in a very condensed fashion, only on the material we have in this course. So you can go on and go on with HPC. There are so many topics, and here we keep it to the, let's say, essentials in HPC, and some of them that also even have stand the test of time. And with this, we basically have seen the basics from a CPU, computing entities, no matter how big the HPC system is. You remember the racks we have seen a little bit here seen already with this element. We have the chips, but of course we have them very condensed together in one machine. And we learned a little bit about the so-called multi-core processor. So these are all cores basically on a chip with high single thread performance, so number crunches, really good cache hierarchies that fuel the cores then also with data very fast. So cache is, very expensive, very fast. And with this, we have really a power horse in terms of a computing entity. And many of the laptops you have today have, of course, multi-core laptops. And if this would be all what HPC can do, then it is, of course, not at all what we consider, let's say, parallel computing with HPC. Hence, what we learned a little bit is then that basically in the last lecture that we want to use these in parallel, and many of them, which essentially looks a little bit like this. You have different processes that then would, be running on this. And of many others that are integrated really in racks. You have seen also the other elements like midplanes and so on. And where you then can see that we have many, many of those available, but they have also very good interconnect. And this was an important, let's say, element in HPC as well. For instance, InfiniBand and so on. These are all, let's say, integrations into a HPC system that makes it really fast to communicate between those processes. Hence, the idea is also then to have some computing or more better saying programming paradigm of how to actually program these parallel processes. And by doing so, we use the standard message passing interface. And as the name suggests, this means you send lots of messages, right, between the different processes. And this is an important part because we cannot access in a larger system the memory from another processor, right? Hence, we call that distributed memory. You see that a little bit alluding here, that every time when a processor here and a core has to, let's say, access a memory space of someone else, it would need to communicate, right? It would need to go over. The own memory is, of course, the address space that you can reach. But as soon as you talk about another processor memory space, it's not basically accessible. Hence, in order to use data from another processor, we have to send messages. And this data can be many things. It can be simple integers, could be, let's say, MPI structs, really larger, let's say, data that we will also see later in the course that you can create in the MPI environment, and so on and so on. So I think with this you'll notice, and you will see also in lecture 2 how we realize this. Then the lecture 2 will be based on MPI, where I show you all the details. But in the moment, I think it's important to just understand this concept that we have this message passing between these different processes that run in parallel at the same time. Now, however, another, let's say, computing paradigm that also stands the test of time, if you want, in high performance computing is shared memory programming. Shared memory, as the name suggests, is quite, suggests it's easy. So you have one shared address space. You see that a little bit here. And then you have many lightweight threads that run, let's say, on all these processes here, in order to, basically write and read and write and read from memory and, do something with the data in between with a program. But you can always store it in the memory, and another thread, as we call them in shared memory programming, can then simply read it. Now, there's this NUMA and CC NUMA, which is now having the cache currency here on the memory interface link, so that it actually looks like it is a one shared memory system. But in the end, it is a similar entity like the shared memory you have here on the left side for the programmer. But the reality is that this cache current link here will also will basically then enable us to see that one shared memory address space. So it is basically distributed memory, if you want, from the real implementation perspective, but it's hidden from us users. That's why we call call this essentially shared memory. Now, the reality is also we combine this both often, right? So there is a kind of distributed memory programming using MPI between different nodes, and then within the node where we have multi-core processors, we use then essentially shared memory programming with a standard called OpenMP. We will also learn later in the course about this. And then you basically can combine the power of both, and we will make the case later in the course. So this were basics, and there were many others, but I think also important to understand is then the ecosystem technologies that came across as well, and some of the applications really that we have. And I think, for instance, the multi-core chip was very different from the many-core chip, which is important for you to understand, especially today as there are many more accelerators, as we call them, GPUs, general processing, graphical processing units. So this is basically something where today we have quite a dominance of NVIDIA, but AMD and others are catching up, Intel and so on, to have also many core processors. What they in the moment have all, let's say, as a shortcoming is that they often need the CPU to fill the main memory and to fuel the device memory of these GPUs in order to do, let's say, data processing. But we have learned, because it's this many core architecture and you have thousands of processors, this is very beautiful for some applications like deep learning networks you see here, for example, a convolutional neural networks or autoencoders, and so on. And the reason is that many of these many core processors, is thousands, are basically not really high single thread performance as we had in the multi-core, right? These are moderate, let's say, paced processors. That's why you can put so many on the chip, because otherwise it would overheat. That were the limits of the multi-core processors, which were nicely, let's say, now changed in the GPU setup. Hence, this is now beautiful to achieve throughput. And when you have something which is a little bit, let's say, as we call it, nicely parallelizable, like the array, for instance, here, matrix vector multiplication or vector multiplication, doesn't matter, and so on, you will see the mathematical rule to here do a matrix vector multiplication is here the orange, and everything else can be independently done from the colors, right, in order to fill the whole result. And if you go deeper into deep learning, what we will do also later in the course, we will realize that many learning steps that a deep learning network will do is essentially nothing else than multiplying these matrix vectors and so on. Hence, the GPUs are just beautiful for AI applications, and also for many of the, let's say, simulations. We see here an earthquake simulation that we have discussed the last time as well. and more packages coming on supporting GPUs, because here and there, if the same instructions are repeatedly again and again and again done, then with other data, then this is also a beautiful technology. And we will have a whole lecture about GPUs, so I don't need to basically talk too much about it. We have also talked about big data, which is handled in several ways in HPC systems with parallel file systems, but also in different areas. We have seen that the HPC system already can digest quite a lot of data because we have parallel computing. We don't have this serial limits anymore. So in a way, there would be no end to scaling, but of course we will also face in the course here and there some practical examples where scaling is not unlimited, although it suggests a little bit by just adding more and more and more computing processors with the storage and caches and so on, we will also face other limits in scaling. One final point here, and that's where also HPC is good, and it's not only training deep learning networks faster, that's what we also will realize in one of the lectures later coming on. We also can learn them better in HPC. And the reasoning is that we can do so-called hyperparameter optimization in a more systematic fashion, having all this computing power. So you see here some of the hyperparameters. I will not go in all the details. You see a typical one is here the optimizer you use, or learning rate and so on. These are things you pick as a human. And with this, you have a large pool of elements to choose from, right? So is it SGD or Adam? Is the learning rate instead of 1, maybe 0.1 or something else? So these are things where the human is making already some configurations. And basically, when you do this, you are not sure that's the optimum for this particular deep learning problem. It could be maybe that this was the best for the convolutional network you see here, but when you then switch to an autoencoder for another, let's say, study that you see also here in our publications, then it might be very well that these parameters are nonsense or basically don't give you good accuracy. Hence, we have a way called hyperparameter optimization. If you notice, we integrated this nowadays in the course as one of the most newer lectures because it gets more and more momentum. Why HPC is also useful in AI, basically to pick this hyperparameters well instead of just the human. And of course, you could go on with HPC. I just make the final comment on the quantum computing, which is now active. We have several quantum computers already procured within Europe. So they are existing and people do their baby steps on them. We have first initial applications. Also my team, we publish a lot on, D-Wave these days. For instance, one specific quantum computer. There are many others, many other types. But of course, we also cannot go in a HPC lecture very deep into quantum. It needs a complete different lecture as well. So this was a little bit more longer than usual, just because it is the basics and you need to know the basics. So when we come now to all the lectures, which will be now following, you will see we will dive into parallel programming the next couple of lectures together. Here with MPI, distributed memory, but then also quickly go to shared memory programming with OpenMP. So this is all building on lecture 1. That's why it was essential to actually see that. And also when we do then this 5, 6, 7 lecture together, you will see what we just discussed with the many course will be an important aspect of it, why basically deep learning is so powerful. Hence, let us go to the idea of the lecture today. And this is really briefly having an idea of how you program and compile a C program. This will be, of course, part of your assignment later, but it will be, let's say, not C programming for the sake of C programming, but rather for the understanding of parallel computing. Hence, you don't be afraid if you're not a typical C programmer and a Java programmer or Python. Here we do really basic steps. The importance is that you understand the HPC systems module environment, that you have to load the relevant compiler, for instance. And I know that some of you maybe not even used the compiler before. Many people use Python these days. So we will execute and basically also compile these C programs on the HPC system. Then we understand that doing this on a login node is not a good idea. That's something coming into place when you think about that we have a multi-user space. And that's why we have also the second part of the lecture where we then talk about schedulers on HPC systems. So we have this huge multi-user systems where maybe hundreds of users use the system at the same time. Hence, we use some HPC system software environments to understand that better. Schedulers are one of them, like Slurm, for instance, but there are many others. Here in the course, we use Slurm examples on our Elia system. But if you go, for instance, to the deep system that we already used, for instance, also in the practical lecture 0.1, if you remember, it would be very similar to execute the jobs there. Hence, it's a sort of modus operandi, which is a sort of standard or de facto standard in HPC systems to use such a scheduler. Even if it's another one in EVM systems, we had load leveler, for instance, a long time, and there are many other schedulers, but Slurm is quite an active one and often deployed in HPC systems today. And then you also understand we're executing these C programs, and with these schedulers enables you that the job is actually run on so-called compute nodes. Hence, we will make also the first distinctions between different nodes in HPC systems, which is a login node and the compute node, and I will show you the difference as part of this lecture. So let's go and start with the practicals. I mean, here it's really an idea that you get some practical knowledge of using essentially Unix again for C programs, for compiling, using the module environment. And with this, you can use high-performance clusters internationally. And of course, also the programming of it, right? Many programs are in Fortran, many programs are in C. So if you are, let's say, in the area of physics applications, this is still a dominance there. If you go to AI applications, you see, of course, much more Python these days. Hence, what I teach you should be a little bit the basics here so that you can build on that later when you want to maybe compile other C programs, which others maybe have provided to you for different applications in engineering, sciences, and so on. We have some examples of those, of course, later in the course when Reza is also partly taking over. So let's go to the practicals, programming, C programming. Here again, the kind of link to the lectures that we have later, starting from CFD, computational fluid dynamics, but there are many others. You see here in Earth science application, terrestrial systems to understand the groundwater modeling. You have basically 3 different codes here that are used together, Cosmos, CLM, and ParFlow. And this is not obvious to you how this is actually all implemented. Important is just to understand that they're all primarily written in C. And then there's a Oasis coupler, which is a 4th MPI program connecting these 3 with each other and sending, also the variables between all these different codes. For you just to understand that all these different areas of science is similar like we have in our national HPC computing, in Iceland, the national competence centers. You see there are many simulation data labs, things that you have seen in our Icelandic HPC workshops. They have many of these codes which are still C, and here's also NEST, which is from the brain sciences, for instance, a kind of simulator for spiking neural networks, and it's also in itself implemented in C++. Just to show you that, of course, this programming language still has basics, and if you go to Earth Sciences, weather forecast, ECW Math, it's basically the center that gives us the European forecast and so on. There are still many codes running in Fortran, right? So it's a very older programming language, still people using it today, and it gets some momentum still today. Just that you know that these is still relevant in scientific computing. If you are thinking about that C might be old or that Java should be everything, just because you learned that in your first couple of semesters here. So in the end, this is about performance, right? So, and as the name suggests from the course, we are after high performance computing. Hence here and there, software engineering, let's say, best practices are a little bit ignored to also get to the best performance. Hence reusable of code, there are lots of things needs to be done here in the scientific domain still, if you look on some of the codes, to be, let's say, in proper software engineering. And the NEST code is a good way towards this. I think it has good, Git labs and so on. And if you want, you can have a look. And in generally, that is, of course, something to consider that C and the compilation is a very fast entity of execution and doesn't have this basically virtual aspect that you have basically from Java or Python as interpreter languages. But again, we come to the basics of programming, and that's not the idea that you come out as perfect programmers here. The idea is rather to understand what's the difference when you program HPC systems. And when we do so, we need documentation. And when you see documentation, we do the earlier cluster. We understand, okay, this has lots of multi-core CPUs for us available where we can execute a C program. And you see already here what I'm saying. There are different compute nodes on the one hand, different elements, and here's a login node, right? And this is something what we also will explore later when we have the second part of the course today. Let's go really to practice, log into Elia. If you remember a little bit, I have here this mobile X term, which was an SSH client, but it does not have to be this one. So they have all similar elements. I need to specify my username, Morris, and then you remember our lecture intensively on private and public keys. I will not repeat this. I think by now you should know what's up with these keys. Hence, I will not go into the details here, but it's important to really understand them. So when we use a private key, sometimes there could be a password request depending on how long you not have used it, or how long you basically had the last session away from the current login that you have. In this sense, this can take a little bit of time, and in many cases, you would say the password is not again needed. So here we wait a little bit on the access to Elia now, so that it should basically come in a moment. And all what I will present, of course, you can imagine is already here. Here's an example also on PuTTY. If you want to use this one, I would still recommend to use the mobile Xterm service. And you have seen here the keys again. If you're not sure yet what was the private key, one of the ideas of assignment 1 will be actually to understand this better. Then please go to the lecture that we had, practical lecture 0.1. So with any luck, we could now log in, and you see here by now we have our public key was accepted. We are in the welcome screen, as it is called. I will increase the font size a bit for the recording. So we are in Elia now, like we did before with the SSH key, so no surprises. A short glimpse on what are the latest news. Perhaps there's a file system problem, or out of system, or basically a kind of, they call it also system maintenance windows, which is important for us to understand. You see here home directory migration. There's different aspects and infos. That's why it's always good to at least skim over it. Also, when you think about support here, this is basically that our systems administrators are not anymore in the field office in Askia. And now we have a new email address here from eray@how.is if there's, let's say, trouble with the system. But in the moment, it looks everything good, basically. So let's get on with some more details what we can do. Again, we are landing in our home system, print working directory, you know that. So I'm basically on Newton here in my own directory. From one of the last lectures, we had the HPC course Spring 25 already created, and that's where we want to go in. And then when we go and check what's there, there's already directory MPI that I created for you here for the recording, with a very interesting cutting-edge Hello World program. So this is obviously in computer science the first that you have to do. The C program is Hello World. So let's move into, and you can do this, for instance, by using the VI, right? So when you have the VI editor and hello.c, you see here it's a very trivial C program. It has one include of standard IO header files, but then there's a main program which will be executed. So we don't even do many functions or anything else. This will come in later lectures down the road when we have existing software explored. But all we do is basically a printf hello world, and then return 0 that the program has actually worked fantastically. So there are a couple of things to note here. Firstly, that this is a proper C program. And an MPI program that we want to develop out of this later is a parallel program, which should be also a proper C program. Hence, this is not in conflict with each other, but you see here clearly that there's not parallel anything, right? So the main will just print out something and then done. So the simplest, if you want, maybe of kind of actions that you can do, but it's already carries some of the essences to use really a HPC environment. And this is something what we also want to explore today in the first part and then later in the second part. So ignore in the moment the submit hello job script. That's something which will come in my second part. Here we want to now see what we can do with a hello C, basically program. For those that are knowing a bit about more Unix, you see also here is no X, so it cannot be executed. When I now say hello.x, hello.c, nothing is working here. So hence we need to compile this to an executable. And this is of course also documented a bit in the slides, moving perhaps also here a bit parallel ahead. So we had the welcome screen. We have the simple C program that I explain you here in all detail. It makes sense to have these folders, right? So when you do your own steps in the assignment, I would recommend you do similar things where you basically have a structure, not put all in one directory, because this could be misleading also for outcomes that you see later from the scheduler. And hence we need now a C compiler that you have seen, because we cannot execute just the C program like that. Hence, we come back to our elements we already learned, and this is the system module environment. If you remember, we had it the last time in the practical lecture 0.1, where we have different modules. And if you remember, one way of doing it, make first clear and maybe increase the font size still a bit, we can do, for instance, module avail, right? What you now have is all the modules which are installed on Elia here on the system. And while many of them are important, NVIDIA for CUDA to use GPUs properly, for instance, or different elements for applications are there, which is for us important. Parallel I/O viewer, HDF, is a hierarchical data format, and this is a parallel I/O on HPC, system to really enable the throughput with data. And many others that you see here. OpenFoam will be something where Razer will talk about later. So this is computation fluid dynamic codes that you can use for different areas. For instance, in the Met Office, they do avalanches with OpenFoam, right? So many of these are a bit like application oriented, but many of them are also, let's say, low-level libraries that you need really for getting the system up to speed. Examples are from the CUDA environment, for instance, for GPUs already mentioned. So for us important, however, is MPI. Hence, we see there are different versions of MPI, and one is on OpenMPI, which we basically also will allude to in the next lecture, lecture 2. But this is the one we're interested in. So here, apparently, this comes already, with a C element in it. So we want to module spider this. Hence, you could, of course, go ahead now and say, use another C compiler. But I use basically this environment already to go to the next step in practical lecture 2.1, where we basically do the same thing in order to then really, compile an MPI program out of a C program. So, and I don't want to give you several different ways. As a beginner of this course, at the beginning, I think it's good to have one modus operandi so that we can see here now that we can directly load this module, and that is what we should do, module load. Remember the marking here and then the right click, for instance, this enables us to copy paste that we want MPI in the OpenMPI 4 version, specifically for 4.1.2. Now I have loaded this module and can go ahead with compiling. And this is all, of course, also here somewhere on the slides documented, right? So what we now do there is MPI-CC for compiling a program. Here, it's not the ping pong C, it's actually the hello C. And the -O option here is essentially for us an hints to a proper naming scheme. And I would recommend to do the same when you do your assignments and so on, because otherwise you lose a little bit track if you don't have a specific output how this executable should be named. So we have done this module load, and we'll use now essentially MPI CC as we had seen, but before we have to maybe look again what's happening in the directory. So we have the Hello C program here. So now we can use MPI CC because we have load the module. We use essentially here the -O option for hello, and what we want to compile is the Hello C program, right? So by doing so, we should see now that there's an executable created, which looks a bit different, not because it's green, but you notice that the X's are here. So this is basically marked as, an executable. So hence there should be something happening if we do it. And for instance, if we do now, let's say hello in the same directory, hello, bam, you see hello world is given out directly on the screen. That is also important now for us to understand. When you're not using a scheduler, when you're not basically using the HPC environment as you should do, you actually work now on the login node and executing on the login node. And of course, this is also sort of a serial execution because there's no parallel computing yet. And we're also not on the compute nodes. Hence, we miss still a couple of things that will come in the next couple of lectures, like MPI. Then we use a scheduler in the second part of the lecture. So let's look a little bit what we have done. We have now this nice executable that, we have is a C program, a valid C program. And this is already a big achievement for us in the moment. In a way, this is, of course, as I said, missing with the MPI. We will do this after we have now learned the conceptual details in lecture 2, what the MPI is really. You just got a high-level intro, so we will look in this more detail. A short glimpse for it, it's that it's a standard for message passing, as the slide suggests, and that there's an implementation to it, right? So this OpenMPI implementation that we have seen and loaded in version 4. And we use this with the MPI-CC compiler, and you can also use when it's prepared with other environments and compilers, other tools. But here we want to keep that in order to make a relatively streamlined access for those that are never programmed in C, for those that never use a HPC system before, to keep the learning curve, let's say, not too steep. We have also done this. So just a slide for summarizing here really. Again, the module avail and the module spider commands, which are very essential, right? You see here something which is very easy to load, mostly because you have also the point that it has no dependencies here. So you see that we module spider it, this MPI OpenMPI 4. There's no other modules that you necessarily need to load. In normal system software, that's not usually the case. You would have, let's say, for advanced programs, really a long dependency list. Hence, you end up with many module loads. And we will see that throughout the course when we come to more applications, also in AI, for instance. You need to load a couple of different elements, not just Python. You need also, for instance, tool sets like TensorFlow that are basically enabling you with a Python then program to enable you also to use deep learning networks and so on and so on. And this is really done in many of the applications. In former times, we had also, for instance, HPDP scan as one of the module available. Since we do more and more deep learning in the courses, we skip a little bit this clustering as technique, but this is also a C program which is used for, let's say, unsupervised learning, where you cluster then, for instance, here in the brain slice that you basically have as an image, and then you cluster essentially different areas of it and come to different cortical layers. And this is just to show you an example again from brain sciences, but a complete different example from NEST, right? So NEST was more, let's say, a code which was for the spiking networks. And here we have really just an idea of how to use a clustering algorithm, which is essentially usable in all different fields in engineering and science. but here we're using it in brain sciences. And this is sort of a distinction also a little bit from the AI perspective. So these AI tools, machine learning, deep learning, but also here more traditional algorithms like the DeBi-scan algorithm, for instance, that one of my PhD students had also parallelized really effectively. So I would say it's still one of the most scalable DeBi-scan algorithm on HPC systems. So this is something where where HPC then is used in C programs and is also making use of MPI and shared memory as well with OpenMP. And I will keep this lecture example a little bit so that you get a better understanding what you do usually with all these different codes, and that not all of it's maybe these days with AI, deep learning, and machine learning, that there's still some algorithms like clustering, for instance, very essential in science that enables us also to understand the broader portfolio, that HPC is not just used for deep learning. So we have used the right modules for the MPI compiler. We compiled essentially the C program. You have seen this in the executable. But what we have done there then was executing the hello on the, let's say, login node. And this is my last statement for basically the first part of the course here. This is not the idea, right? So here we compiled, and this is fun, and this is okay. But the execution should be usually never done on a login node, right? You will see that when we log in with SSH, we are here located. Hence, everything we do is automatically operating on this login nodes. But when we want to run jobs, let's say in a typical production system, thousands of CPUs in parallel with MPI maybe, then we talk about compute nodes. Right now, Elia has also compute nodes, maybe not in the thousands, but still a reasonable number to get the teaching done. And with this, you have basically the opportunity to use these compute nodes for execution of applications, but this requires a so-called fellow called scheduler. Hence, you can think about that our next course part here is really called scheduling, where we understand how we actually use these compute nodes instead of doing everything on the login node. Now, when you do, for instance, complex, climate simulations, for instance, you would be on the login node and you started there, and basically you would even maybe get calls from administrators which say what nonsense you are doing there, right? So please hang on and see also the second part of the lecture where we then do it properly, the hello world execution on the compute nodes by using the Slurm scheduler. So see you then.